Okay. Like that music. I'm a little under the weather, but I'll try to get through this session with you, and hopefully I won't share the joy with you. Anyway, what we want to do today is we want to talk a little bit more about transformations, and this is kind of the starting point for understanding this material, and we'll continue to use these things throughout the course. So it will become automatic for you with a little practice. And then we want to start doing some real stuff. We want to start modeling using our algebra skills, the things we've been learning in the last few weeks to actually tackle some real type of problems, and we'll just take some problems out of the textbook to do that. All right? So let's go ahead and let's do a couple examples with transformations to sort of see the pattern that exists no matter what f of x you pick. So remember, what we're starting with is some function, and we could call this the old or the elementary function, and we then want to take something or make it more complex. So why don't I start out with something more complicated than just a simple function from our library, and then let's see if we can see what these transformations are that exist in that. So here is a new function. Let's say, and you pick one. Pick one of those out of our library. We had a variety of them we've summarized before.
Y equals x squared.
Okay, y equals x squared. So I'm gonna make it fancy. Let's say it's minus 4 times x plus 2 squared minus 10. Now, does everybody agree that this is an x squared kind of a function? Is that comfortable for people? Okay. While we're at it, let's apply the same transformations. Now, what are the transformations that you see that happen to x squared here? What are the items that you see here that cause the transformations? The negative 4 and the minus 10, right? Okay. Those numbers are the things that cause the basic x squared graph that you're familiar with to be transformed. Okay? Somebody else give me a different one of our library of functions. Cube root, okay. Y equals minus 4 cube root of x plus 2, and then off the tail end of that, subtract 10. Same basic type of idea, isn't it? Same transformations, except applied to the cube root function. Notice what's underneath the cube root, the x plus 2. Over here, what's inside the squaring function is x plus 2. And then on the outside of that, you observe these other numbers, minus 4 and minus 10. Okay, so look, they look pretty weird, pretty strange. Now, notice that the old function from your library is, the basic character of this thing is a y equals x squared. So this is your old function down here from your library, and up here is the new function that we're trying to understand. Similarly, over here, the old function is y equals cube root of x. Now, next to the old functions here, we could draw a little micro sketch. Here's your x squared function that you've got in your head. Over here is your cube root function that you may or may not have in your head. Although once I show it to you again, or you see it in the book, this is not x cubed. This is not the cubic, right? This is the cube root. And if you don't have it in your head, here it is, looks like this. All right, and this is one of them that's in our family. Everybody okay so far? Jennifer?
I thought it was more flatlined in the middle.
What do you mean flatter,
Yeah.
but still having this character though, right? Okay. Now, for instance, if I went out to 27, if I went clear out here to 27, how high up would that be? Cube root of 27 is
3.
3, right? What times itself 3 times gives you 27. This would only be up 3. So you can see I've sort of exaggerated the scaling there just so we can see the graph nicely.
But
Okay?
it would follow the y-axis a little bit more than that, right?
It would, excuse me?
Wouldn't it? It would follow the y-axis a little and get a little straighter there, wouldn't it?
It actually, if I had equal scaling, like if this was 27 here and that's 27 there, then this thing would look almost like a flat line and you'd hardly be able to see it. Right? Is that okay? All right. So anyway, you want to have these fundamental old functions in your head. You look at the complicated thing and you go, okay, the only thing that's inside here being squared up here on either of these problems inside the actual basic function is x plus 2. And over here, what's inside the cube root function is x plus 2. What's outside it is really an adjustment that's happening to the y value, these old y values here. Now watch this. Can't we do a little bit of algebra up here on this complicated thing? See, what's going to happen is we're going to have complicated looking equations like this, functions like these, and we want to be able to quickly sketch them. So with arithmetic, can't we bring this 10, can't we bring that subtracting 10 over to the other side? And it becomes y plus 10 equals that. And then over here, we can bring the 10 over similarly. Right? And notice that 10 is outside of the actual character of the function. So now, I brought it over here. Now we also could do something with this negative 4 to move it away from this quadratic expression. And we could move the negative 4 off of the cube root expression by doing what? Divide both sides by negative 4. Divide both sides by negative 4. If we do that, the thing is going to look like this. And similarly, on the cube root function over here, y plus 10 over negative 4 is equal to this cube root function. Is that all right? Isn't this y up in here, all the way through here? Isn't this y this new y? Right? Aren't these the new y values that are going to show up when we draw the picture? These are the new y's. And so look what's happening compared to the old y's down here. Isn't this old y being replaced with this new y plus 10 over negative 4? Do you agree? Aren't we taking this thing right here and replacing it, this thing, and replacing it with all of this? Does that make sense? All I did is arithmetic up here to get this thing to look like this. Okay. And all I'm doing, what am I doing to this old x?
Plus 2.
I'm replacing this old x with this new x plus 2, right? Right? Now look at the math. Let's just do it. Take this thing on this y stuff right here, multiply both sides right here by negative 4, and so we have negative 4 times the old y is equal to the new y plus 10. And now go ahead and solve this for the new y. I'll just write the new y on the left because that's the way we usually like to write the thing we're looking for. The new y is then going to be equal to negative 4 times the old y if I subtract 10 from both sides. Doesn't it look like this? Right?
I don't understand why you're using old and new. That concept is just escaping me.
Okay. This is old stuff that we're real familiar with. This is something strange, right? Okay. And so I'm just calling this something new. We're familiar with this. We're familiar with y equals x squared and what it looks like. Its domain, its range, its critical key points like its vertex. So we're familiar with this thing. Really, we're very comfortable with this. We're trying to become comfortable with something like this. I'm just calling this new. So when we draw this picture, we're going to have a new x values associated with, and then associated with those new x values are new y values. So the picture is going to look different than that thing. Okay? And a bunch of you probably had the same question she just had. Why am I calling that the new and this the old? Is that okay with everybody? The math here so far is real simple, isn't it? You're just not sure why I'm doing what I'm doing, right? Now look at what this down here is telling us. If this old y is being replaced with this, and I solve for what this new y is, look at what it's telling us happens to the old y's. Don't we multiply the old y's times negative 4? So what's that going to do if I multiply these old y's times negative 4? It's going to take these old y readings, which are these y values here, the heights, and these are our old y values, and it's going to multiply them times negative 4. It's going to make them 4 times as big, isn't it?
But upside down.
And upside down. You with me, Todd?
Oh, yeah.
Okay. And so what we're going to get is if I do just that part of it, it would look like this. Tall and skinny, 4 times as much everywhere. But upside down, right? Negative. And then, what do I do here? Subtract 10. What's that do to all these y values here? If I take 10 off of these y values, what's that do to it? Help me. Down, doesn't it? Doesn't it take them down 10 more? And so what happens is these old y values being up here, these are the old y values, these heights here, it's going to be hard for me to fit it on here with my scaling, but it's going to be tall, skinny, upside down, and then down 10. So it's going to be sitting down here like this. So here, these are now the new y values here. At the same time we do that, what happens to the x's? What are going to happen to the x's?
You're going to move them to the right.
Okay, look at now let me see if I can tuck this in to get it on this board here, which is a fairly small board to work on. Isn't this new x going to be equal to the old x minus 2? So what am I doing to all these old x readings that you see right here?
Move them left.
I'm going to bring all these x's readings that you see, I'm going to bring them to the left too, including the ones over here. They're going to come to the left too. Question?
Is the point of this to simplify the y we were given?
The point is to have us have a quick sense of what this picture is going to look like.
Can we do that without doing all of that algebra?
Yes. Once you understand what's happening here, and I'm showing you the details so that you don't just blindly believe me and say this turns it upside down and makes it 4 times as tall, and this causes it to jump 2 to the left and down 10.
That's what I thought we were
Yeah.
down.
Yeah, and if you got that skill, you're okay. You're fine. That's the way I do it, what I just said.
That other brings me.
But I'm explaining why it works the way it works, and that may confuse some of you. Okay? Is that true? Okay. So I'm showing you why it does what it does. It's kind of the background, it's the detail as to why it does what it does. So what we've got, in a quick sense, let's see if this will show up on the screen, I think it will, is I'm going to take and distort my graph by realizing that I have to take the old y readings on my parabola, my simple parabola, I have to make them 4 times as great and negative. So that's going to make it tall and skinny and upside down, and then it's going to get drop 10 and then 2 to the left. So my picture then is going to come down over here, 2 to the left and down 10 and be tall and skinny pointing downward. That's a quick sketch of this function, of this thing up here. Hang on just a second with your question in the back. Let's do the same darn thing with this cube root over here. Aren't the transforms identical? So what's going to happen is this cube root graph is going to be 4 times as tall. So it's kind of getting vertically stretched, 4 times as tall. It's going to be turned upside down. And it's going to be kicked 10 down and 2 to the left. Quick sketch. 10 down, 2 to the left. And it looks like an upside down cube root that's been vertically stretched somewhat. And I'd label this point -2, -10. Getting it? How many of you are feeling like you're starting to get it? That's a good sign. The people I'm worried about are the ones who didn't raise their hand. Okay. Okay. Yes,
Wouldn't it be
Tyler?
to the left 2 cube root or cube root 2?
It's just, here's why it goes to the left too, right here. You're taking these old x's inside that cube root and you're replacing that with x plus 2, some new x plus 2. So this new x reading plus 2 equals the old x. You're replacing this x with that. And if you look at what the old x is, if you look at what the new x is here, it's the old x readings minus 2. So you're taking all these old x readings here and you're kicking them 2 to the left. Yes, question in the back.
So why did the graph flip upside down then?
Negative.
Oh, okay, times by 4 and then
And then
Okay.
did it also narrow because of the 4? Made longer. So the curve is going to be more pronounced?
4 times as tall, 4 times as tall, right?
So the
'cause
curve will be more pronounced on
Yeah.
the new one.
Well, it depends on what you mean by pronounced. It's 4 times vertically stretched, 4 times vertically stretched, and then turned upside down because of the negative. Okay, now, how can we how can we confirm that what this story I've been telling you is true? We have our,
Accept it and move on.
just accept it blindly on blind faith and move on, right? But let's grab our graphing calculator and see if it does that. And here you'll see why I want you to be able to do this in your head. Is because then you're going to turn this on with your calculator and you're going to see something interesting here. So with the graphing calculator, we go up to our function set and let's take and enter, which one do you want to do, the parabola or the cube root? The cube root one? So we use our negative key, -4, and then you go to the math key, Math, item number 4. Inserts the automatic cube root function into your calculator. And then inside the cube root, we're going to put our x plus 2, and then we're going to subtract 10 from that. Okay, now when you're using your graphing calculator, what do you do after you enter the function? We just entered the function. What's the next step? We think of a viewing window. We think of a viewing window. We use our brain. So I hit the window key, and I've got an image in my head based on that algebra we did. So it looks to me, if you go back and look at your notes there, it looks to me like this graph's going to go off to the left pretty fast. Doesn't it? If you look at that picture of the cube root, it's going to go off to the left pretty fast. So I better set a window pretty far to the left. So why don't I say minus 30 as a first guess, and then I'm not going to go too far to the right. Why don't I say 10 to the right and put tick marks every 5? 30, negative 30's on our left. So we have a spread of 40 across our window. Now vertically, we're dealing with a cube root function, so we know cube roots don't rise or fall very quickly, but we are magnifying it by a multiple of 4, aren't we? So it's going to go up and down quicker than just a plain cube root would. So I'm going to go ahead and just take a rough guess. How about minus 20 to 20 and put tick marks every 5? So this is our first educated guess for a viewing window. Okay? Educated guess for a viewing window. So now I hit graph. I run out of batteries? Okay. Got a dead battery. So okay, we got the sound back? Okay, good. So what I did, folks, just if you missed that, the DVD, we took an educated guess on the viewing window based on the paper sketching or sketching we did on the board, and then I hit the graph key once I had this window set. And I get a picture looking like this. Notice what's nice about this image you see. There's a lot of nice things about it. It's lovely, thank you. Okay, what I mean by nice is, doesn't it show what's called the end behavior? It's showing that it's rising slowly as it moves off to the left. It's also showing other details. It looks like it's got a 0 here, doesn't it? Somewhere here, a 0. And then it looks like it comes down and it goes through a very important point down here, doesn't it? What? Well, hold it. What point right in here is really important to us?
Oh, a local max?
No, there's no local max there. Look, think about what we've been doing. Huh? There's a spot here. What is this spot based on what we talked about a few minutes ago? Negative 2, negative 10. Negative 2, negative 10. And then it continues to fall and then moves off to the right, dropping slowly. So it's got the end behavior. End behavior, falling slowly to the right. Oh, it's also got, as somebody mentioned a moment ago, a y-intercept. Okay, now what I want to do is, actually I think we'll live with this window. That was not too bad of a guess. Okay, so watch this. If I now turn trace on, I can sort of check to see if my transform information was good. If I insert negative 2 in my trace key, it shows me right on negative 10. Okay, very nice. And I like the combination on the video there. It's got both the board and what I can move my hands around in the air here too. Okay, so what you'll observe is you can see that very important point, negative 2, 10. That's that transformation. And every other point on that graph has been shifted 2 to the left and down 10. Now let's come back up to the board. Let's come back up to the board and take this function again and look at it.